Our goal today is to delve into a novel approach to regression analysis. Specifically, our primary attention will be directed towards the ridge regression technique, and additionally, we'll thoroughly examine the principles of both Lasso and the elastic net methods. Well, these types of analytical tools ought to be quite comparable to the ordinary least squares method. However, we will be able to exert a significant degree of control over the specific parameters, or indeed the coefficients that are estimated in relation to the independent x variables. The fundamental concept we are addressing is the critical need to enhance our out-of-sample forecasting capabilities. Let's begin by reviewing the basics. Imagine we have a regression model where our dependent variable y is explained by many x variables. In this particular scenario, if we opt to employ ordinary least squares, and considering that we're specifically engaged with the time series regression analysis, it implies that we possess t distinct observations. Consequently, we'll have a primary time series variable denoted as y alongside an explanatory x variable. The resulting statistical model will then take on this specific form. Simply, the independent variable x is multiplied by its respective coefficients, such as beta 1, beta 2, beta 3, and so forth, and any remaining portion of the dependent variable y that cannot be explained by these factors, this is what we call the error term, which is typically assumed to be independently and identically distributed. What this means is that we are referring to errors which are independent, identically distributed, or more simply, what we call white noise. Each core principle behind OLS is to determine the coefficients that effectively minimize the overall error. Therefore, this represents the primary objective function. The error term is simply the difference between the actual observed y variable and its predicted value. This predicted value is often referred to as y hat. You begin by isolating the error term, which is precisely the expression found enclosed within the parentheses. Following this, our next step is to square this particular value, and then our objective becomes to minimize the overall sum of all these individual squared errors. The final mathematical representation of this process will appear exactly as shown here. For instance, let's assume we're dealing with a very small data set containing only 4 observations in our time series. We'll also have 2 predictors. These are typically designated as x1 and x2, and the final part of our model is always linked to the constant term, also known as the intercept. So, these x variables, along with the constant term, are all stacked together to form a matrix that we call x, and then separately we have this one, which is the y variable. And then we will want to estimate the coefficients. The very first step we need to take following this particular equation is to determine the product of our variable x with itself. Therefore, what we do is we first transpose the matrix x, and subsequently we proceed to multiply that transposed matrix by the original x matrix. And when we perform the operation of transposing the x matrix, the result we obtain is precisely this one shown here. When we're multiplying by the variable x, we are then presented with these 2 distinct matrices. And to perform this matrix multiplication, the established method involves taking the entire first row and multiplying its individual elements by each successive column of the second matrix in order, and we obtain a total of 3 distinct numbers. All right, let's take a look at our first value. In this particular column, the initial number we're working with is precisely 4. Now, to proceed with our calculation, we then take this specific value and perform a multiplication operation. We're going to multiply it by the corresponding entry found in the second column right here. Upon completing that step, the outcome we arrive at is exactly 10, and that, as you can clearly see, represents the total sum of x1. This represents the total sum of individual units, and its purpose is to accurately determine the precise quantity of observations that are present. For instance, if we happen to have exactly 4 observations, the resulting sum will ultimately be precisely 4. So, the concept for this first column is simply to determine the total count of our observations. Then, for the second column, we take this particular row and multiply it by this specific column. This calculation gives us the overall sum of our first variable, which is x1, and that x1 variable is precisely what you see here. And for the final calculation, we will then obtain the total sum of the second variable, specifically named x2. We're going to follow the exact same procedure. We'll then take the second row and once more multiply it by every single column. So the very first number we're looking at in this particular sequence of calculations is going to be the value of 10. And this specific number, as we've established, represents the total sum derived from our x1 variable. If we look at the second row, specifically the second column, we're going to take this value and multiply it by that one. This operation will then provide us with the total sum of x1 squared.
This is the second item.
And for the final calculation in this series, we will determine the product of our first variable x1 and the second variable x. 2, we take the value of x1 and multiply it by x2, then we sum those results together. This calculation will give us the final number we are looking for, and then we will repeat exactly the same procedure for the third row, applying it to each successive column in turn. However, this specific calculation is directly related to the x2 variable, so the result will be the overall sum of x2. That specific numerical result is exactly the same as this one, which is formed by taking the product of x1 and x2.
And the result we're looking for here should precisely be the total sum of each individual x value, specifically the second one, after it has been squared. Therefore, by following this procedure, we are now successfully deriving these specific numerical values.
Our next step involves computing the second crucial component, which is derived from multiplying x by y. Once this operation is successfully completed, we then obtain the very first resulting element.
And that will be the complete and total sum of y. That is simply the overall definitive sum of y.
First, you'll need to take the second row of values, and then you'll multiply it by this specific factor. The result of that operation will be the product of x and y. Specifically, it represents the x component multiplied by the y component. And for the third calculation, we will determine the resulting product of x and 2.
And also y.
So we've successfully obtained the individual elements that make up our second component. Next, we proceed to calculate the inverse of the result we've just acquired. Therefore, it's absolutely necessary for us to compute this inverse value. The fundamental principle guiding this inverse operation is to effectively eliminate any unwanted overlap that exists among our various predictors. It is essential that we observe distinct and independent variations within the x variable so that we may accurately predict the precise degree to which the y variable is influenced by every individual change in x. Therefore, we need to account for the fluctuations of the other independent variable, and this can be effectively accomplished by performing a matrix inversion prior to multiplying by this particular term. This particular term, to clarify once again, illustrates the precise way that y interacts with x1 and with x2. And that particular part will then give you the constant value, because when we actually multiply it, that will effectively take the average value of y, which is essentially like the constant term. So prior to multiplying the terms associated with y by those associated with x, it's essential that we first calculate the inverse. This step is crucial to ensure we effectively eliminate any potential overlap between our predictors, x1 and x2. We first calculate the inverse, and then we proceed to multiply. And by multiplying these values together, we will obtain 3 distinct numbers. This then represents the constant term.
For our current discussion, we'll designate this first item as alpha 0. Then the subsequent component we'll refer to as beta 1, and a third distinct entity will be known as beta 2.
It also is beta 2, that this particular value is specifically for the second predictor, then beta 1, as expected, represents the first predictor in our equation. And this final term here is simply the coefficient, which is also known as the intercept value. Then, after we have successfully obtained our complete model, it's crucial that we carefully find and then thoroughly assess the error term to accurately determine how well the model is truly performing. So, when we undertake this process, we take the actual predictor variable and carefully fit it with the aid of a coefficient estimator. Following that, we proceed to estimate the predicted y values. These particular y values are precisely what our estimated model yields for us. The question is, do these particular values, the ones we've derived, truly match up with the actual observed y variable? If they were to align perfectly without any discrepancy whatsoever, it would unequivocally signify that you possess a flawless, ideal in-sample model. However, in all probability, it's far more realistic to anticipate that we will encounter some noticeable deviations from the true underlying actual values. So, these are the predicted values for each of the individual observations. It's important to remember that we only have a total of 4 distinct periods within this entire time series. So in light of that, we are going to calculate the error for each specific period, and we have them. First, we take each individual error and square it. Then, we sum up all of these squared error values. This calculation will provide us with a clear understanding of how effectively our model is performing. A higher resulting value indicates a greater overall error magnitude for the model, regardless of whether the original error was positive or negative. Any instance where we observe a significant deviation from the precise actual value inherently signifies that the predictive model was unable to perform its intended function with absolute perfection. Consequently, as the error increases, the value of the error squared also becomes greater, and thus the total sum of the squared errors will be higher. Our idea here is that the OLS method will automatically choose the specific coefficients that we had previously estimated in such a way that it will effectively minimize the sum of squared residuals. This specifically is what we refer to as the sum of the squared errors. So what we did was to carefully select the best possible coefficients. These coefficients were chosen precisely to minimize the total sum of the squared values of all these individual errors. However, it's important to remember that these are only the in-sample errors.
So let's take a look at an example where we have an x variable and a y variable.
So what we're attempting to do here is to fit a linear regression model. And this particular model, which is essentially a straight line, is carefully fitted. The goal is to minimize the overall error, specifically the amount of deviation each data point has from that line. However, the objective function, as it's typically defined and used, doesn't inherently provide any direct indication or measure concerning its performance in terms of out-of-sample forecasting ability. For example, if we take the model and then we introduce a fresh set of x variables, specifically after the initial 4 periods have concluded. So, for instance, if we were to extend that sequence further, we would then consider periods 5, 6, 7, and 8. So, we took the first 4 observations available to us, and we used them to calculate the coefficients. We successfully did this, and from those calculations, we were able to estimate the values for beta 1, beta 2, and the constant term. Would it be possible for us to then proceed and effectively integrate these particular findings into the designated out-of-sample variables associated with our primary dataset X? You can, and in this specific scenario, we are actively employing the statistical model to generate a forecast for the anticipated value. Consequently, what we are observing here represents the predicted value derived from within our sample data. Here, if you were to substitute these specific numerical coefficients into the corresponding x variables for the 5th, 6th, 7th, and 8th periods, then we are going to obtain the predicted value from the sample data. Considering the error, would you say that result appears to be lower or perhaps higher? It will most likely be higher, primarily because the statistical model is being fitted directly to the very same n-sample data points. This means it utilizes those n-sample observations for both the independent variable x and the dependent variable y, thereby ensuring the optimal possible fit specifically for that particular dataset. However, this particular analysis fails to adequately consider the full range of x and y values that exist beyond the confines of that specific data sample. It's quite possible that the values of those model parameters could be different. Therefore, if we were to repeat this entire analytical process once more, incorporating these additional 4 data points or observations, it's highly probable that the resulting coefficients within our model would indeed show some variation. And if conditions change beyond the scope of the sample, then the resulting error will become significantly larger than the initial n-sample error. In this case, ridge regression might present a valuable alternative solution. It shares fundamental similarities with ordinary least squares, OLS. However, a key distinction is its incorporation of a penalty directly applied to the size of the coefficients. When we perform an ordinary least squares regression analysis and then observe a coefficient that is notably large, this often indicates a potential issue. Our statistical model might be overfitting the specific n-sample observations used for its estimation. So again, let's imagine a graph where we have our x-coordinate here, and then we also have our y-coordinate over here. Now, if you were to plot a line with a truly immense slope, in order to absolutely guarantee that we can successfully capture the lowest possible margin of error, this approach will demonstrate its effectiveness when applied to the n-sample. The ridge regression technique is specifically designed to carefully manage the inherent trade-off between the potential for overfitting within the observed n-sample, which might minimize error on that specific data, and the crucial ability to accurately forecast outcomes on new unseen data points. In this case, we cannot get too much accomplished or achieve our desired outcomes without significantly increasing our available resources and re-evaluating our current strategy.
We shouldn't allow ourselves to get too deeply involved with the n-sample,
and therefore we cannot have large magnitudes for beta, because possessing a substantial value for this coefficient implies that it's highly probable that data outside our original sample will exhibit a different coefficient. It would likely be lower in the next period. So it becomes necessary to incorporate a penalty to mitigate the risk of overfitting. Our enthusiasm for minimizing the error observed in the n-sample must be tempered, particularly when such minimization is achieved by employing excessively large values for beta.
The ridge regression method will assign a penalty term, and that specific penalty is determined by the value of lambda. So, a substantial lambda value is typically employed as a mechanism to prevent the issue of overfitting. However, we must be careful not to select a lambda that is excessively large. This is because an extremely high lambda value would inevitably lead to the undesirable outcome of underfitting our n-sample regression model.
So, what we do is allow the coefficient to take on any value here in order to minimize the sum of the squared errors, which is represented by this particular part. However, if we proceed with that approach, then we are going to encounter a penalty on this other side. So it's crucial that we strike a careful balance between two key objectives. We need to minimize the error observed within the n-sample, and simultaneously we must avoid estimating coefficients that are excessively large.
So the beta here, estimated using this equation, looks similar to the first part regarding these two sections.
However, we now have a new component to consider, which includes lambda and the p. The p specifically is the penalty matrix, and if we are working with three variables, such as the constant x1 and x2, this means we will need to estimate three distinct coefficients. So what this means is that we will need to have a dedicated column for the constant term, then another separate column for our first independent variable, x1, and finally a third distinct column will be required for the second independent variable, x2. You'll observe that for this initial column, we don't actually have a penalty term. The fundamental reason for this approach is that we do not penalize the intercept value, primarily because the intercept itself does not undergo any change. Instead, our penalty is specifically applied to the coefficients that are directly attached to our independent variables, x1 and x2. So let's take a brief moment to consider this numerical example. So if we were to assign a specific value for lambda, let's say 2, then the next step involves multiplying our designated penalty matrix, which, as you can see, takes on this particular form, 0, 0, 0, 1, 0, and then 0, 0, 1. We multiply this entire matrix by the value of 2, and subsequently we proceed to add the resulting product to the
X when it's multiplied by itself.
And once we have successfully executed that particular step, we then move on to complete the identical process. It's crucial to observe at this point that the numerical coefficients are not nearly as excessively large as they were in our prior observation.
Let's take, for example, the ordinary least squares coefficient for our variable x1. Its initial value was recorded as 1.35. However, upon reevaluation, we observe a significant decrease, bringing it down to 0.91. In contrast, if we look at another instance, the OLS value was 0.71, and it consistently maintained itself within the same expected range. So the primary objective here was to successfully mitigate the overestimation that we observed within the beta 1 parameter. This was a crucial step for our analysis. This specific value, 1.35, appears quite substantial when compared against the other numerical figures we currently possess, indicating a significant deviation.
So the ridge regression method, by applying its inherent control mechanism, effectively lowered the value of the estimated beta 1 coefficient.
Now, the intercept changes, even though we did not directly apply a penalty to it. The reason for this occurs whenever we modify or adjust beta 1 and beta 2, the intercept's value will inevitably be affected. This is because, in the end, there's a fundamental balance or an interdependence among all these coefficients. So, if you were to increase the values of beta 1 and beta 2, it's important to note that the intercept term will inevitably be affected. And the same principle applies in the opposite direction as well. Now, moving on, if you proceed to calculate the error term within the ridge regression model itself,
it is possible that we are going to have higher in-sample error. The underlying reason for our current approach is that we must include a penalty term.
You take the beta 1 squared, the beta 2 squared, then multiply their sum by 2, and then you add that to the error term of the regression. So it's higher than the OLS, but hopefully the model's out-of-sample forecastability is better.
Now, when we consider Lasso regression, the underlying principle remains quite similar. However, instead of applying a squaring operation here, we choose not to square the terms. Instead, we simply utilize the absolute value. However, the fundamental concept stays consistent, that larger coefficients ought to be penalized. But we are not penalizing the squared coefficient. Instead, we apply a penalty to its absolute value. Therefore, this is essentially about geometric considerations, yet the core principle remains unchanged.
Now, in the context of Lasso regression, due to its use of the L1 penalty, which specifically doesn't involve squaring, some coefficients can become exactly 0.
The reasoning here is fundamentally about geometry. If you don't perform the squaring operation and we're dealing with a coefficient that has a very small numerical value, then the Lasso model will simply remove it from the equation.
It's not ideal to have a very small coefficient in our model, because if we were to square that value, that squared term would then become extremely minuscule, so much so that the ridge model would hardly notice its inclusion, given that the associated error term is so negligible. But because we don't square that term, we end up retaining a value that is quite small. However, it's generally much better to completely remove such terms from our regression model. So the Lasso method here will primarily focus on and really excel at variable selection. Yes, this is fundamentally about effective variable selection, where we could have coefficients completely eliminated, meaning their value becomes 0. This effectively removes those variables from the model, so the Lasso is fundamentally about variable selection. Certain variables might be eliminated entirely by setting their corresponding beta coefficient to a value of 0. In contrast, for ridge regression, the primary objective is to shrink the magnitude of the coefficients rather than permitting any coefficient to attain an overly large value.
The elastic net, which is our last method, will effectively combine both of these.
It will effectively combine the ridge regression technique, which inherently involves the squaring of terms, and will also incorporate the elastic net regularization method. These parameters essentially determine the degree to which you wish to lean or gravitate toward a particular model complexity. If your preference is indeed to achieve a more significant degree of shrinkage, then your approach should definitely be more heavily weighted toward the ridge regression method, specifically this one we're discussing.
If your preference is for a wider array of selectable options, which means you are allowing yourself to...
Should you decide to discard some of the coefficients, then you would likely find yourself leaning more towards the Lasso methodology.
So, if your primary goal is variable selection, you would lean towards this approach. If your focus is on shrinking coefficients, then you'd favor this other method. However, you can effectively balance these two distinct objectives into a single powerful methodology known as the elastic net. Now, let's proceed to practically apply these important concepts within the context of the finance research domain. Alright, I've already begun setting up the time series configuration right here, and for the data frequency, I specifically opted for a monthly selection, specifying the start year as 2000 and the ending year as 2024. Afterward, I then clicked the Apply to Charts option to confirm. Following that, I proceeded to enable Series A within the system. I allowed it a sufficient amount of time to process, and then I carefully selected the appropriate metric. So, the dependent variable in this specific example represents the individual stock's monthly return, not an aggregate measure for the entire market. This particular configuration is designed to be applied to just one specific company. Consequently, within the interface, under the limited takers section, I made sure to select Apple. And then, in order to successfully apply all of these chosen parameters and subsequently generate the desired data series, I proceeded to click the Apply Filters button. So, a new data series, which we've designated as A, was created. This represents Apple's monthly stock return. For Series B, we're going to start creating the necessary X variables. The very first one that we focused on was firm level skewness. So within the metric interface that we have here, I specifically searched for firm level skewness, and then by scrolling down, I ultimately selected Apple. And then, as the final step in this entire process to successfully generate the desired output, I proceeded to click on the Apply Filters button. After that, I performed precisely the same operation to establish the X2 variable, which is specifically defined as the standard deviation of the overall dollar volume of trading activity. Next, I also chose the liquidity measure again for Apple, and then I clicked Apply. And as for the final item, I was responsible for creating the 1-month industry momentum indicator once more, specifically for the Apple firm. After I had created the Y and the X variables, I then decided to incorporate the lag of the monthly return as an additional X variable in my model, so I proceeded to the next step. This particular interface is the lag creation box. It effectively displays the current monthly return and has successfully generated a single lag. The job actually finished correctly, so the error message isn't accurate because it simply took an excessive amount of time and the application just didn't like that. But eventually the variable was created successfully. And then I went into the regression model where I carefully selected the dependent variable, Y, and then I also chose the independent variable, X, and from that I got my output. I applied both the OLS method and the ridge regression technique, and then I obtained the findings from both. It appears that the Lasso model, for some particular reason, was overly aggressive and ended up excluding a significant number of coefficients. Therefore, let's now examine the performance of these coefficients when comparing the OLS approach against the ridge regression, which is a well-known shrinking method. For our OLS analysis, I'll now summarize the main results. We worked with a sample of 300 observations. The R-squared value, which is a measure of fit, was quite good at 0.36. In the context of financial models,
This R squared is actually considered very strong, and crucially, it proved to be statistically significant. This is about the forecasting capability, which we've just executed in this demonstration. Therefore, within this particular window, once we have successfully fitted our regression model, we then have the straightforward option to generate a forecast specifically for the most recent 12 months that are present within our data sample.
So, our approach is to utilize all observations, excluding the final 12, to calculate the coefficients,
And then we substitute the calculated coefficients with the x values from the preceding 12 months to obtain the predicted y. Subsequently, we compare this to the actual observed y. And finally, we assess the overall performance of the model. Since the coefficients are estimated from a different time period, and it's in this period that we identify the error, which is the discrepancy between the actual observed value and our predicted y, this inherently signifies that we are performing an out-of-sample forecasting estimation.
So let's go back and review the findings.
So, when we examine the root mean squared errors, which is a key performance indicator, a higher numerical value here fundamentally signifies a greater degree of inaccuracy or a larger error term in our model's predictions. Based on this, we can clearly discern that it is indeed a somewhat more advantageous approach to proceed with the ridge forecast model.
I decided to go with a lambda value of 1. Now, if your goal is to be more aggressive in your model, then you certainly have the option to select a higher value. However, when we look at the RMSE, the results are incredibly close. But from a purely technical standpoint, it is indeed slightly lower when using the ridge coefficient.
And that particular approach, it will actually provide a really significant advantage when we're considering the application of the ridge method. However, the actual difference when we examine it again is truly quite negligible, almost imperceptible in fact. But for the in-sample data, when we consider the overall explanatory power, the OLS model actually proved to be considerably stronger, you see. So I will be able
Let's get the OLS regression run quickly.
So
Let's compute the OLS coefficient, and you'll observe, for example, that the liquidity measure possesses a significantly high coefficient value. Then we should examine what will transpire if we proceed to apply the shrinkage method. When considering the ridge technique, we anticipate that it will consistently result in a lower value. For instance, with the ordinary least squares approach, the specific numerical outcome we observed was negative 1.16.
Pertaining to the ridge,
I think it would be more appropriate if the amount were less.
This is where we can obtain the coefficient. There is no standard error to calculate or even consider in this scenario because quite simply we are directly changing the coefficient itself. So we're not talking about the usual statistical error or the inherent variability of the beta parameter because we have fundamentally altered its value. We are in essence completely changing the coefficient from its original state. Just take a look, for example, at the liquidity measure. It is now completely different and much lower than it was before. Therefore, we are experiencing what appears to be aggressive shrinkage. So, for example, perhaps we should try a somewhat lower value as it appears we're employing an aggressive shrinking method. So, selecting the right amount of overall shrinkage might actually give us much better results when we test it on data that wasn't used for training. Here, we're observing how well the regression model fits the data within our initial sample.
and we have a comprehensive discussion of the errors presented here, which you can then use for comparison. If you wish to perform the out-of-sample analysis specifically to obtain the results that I've demonstrated for you here, you simply need to choose a specific duration, such as 12 periods or any other time frame from the available sample data that you wish to forecast, and then at that point you can proceed to execute the process.
I believe that concludes our presentation for today. I truly appreciate you listening.